So yeah, not just me, you too, hecklers. Please go for it. I love a fight. Let's just talk it out. We'll all learn something. It'll be great. So before I get started, it's kind of ruined my little confession here. But I'm a functional programmer, right? I by choice write Haskell, I write PureScript, I write Elm. And that gets a lot of ridicule in PHP particularly. One man at the back, who's now not looking at me, said there are two types of code, functional code and code that works. And like, I guess the usual reason is like functional programming's never given us anything useful except MapReduce and units and all these things we do day to day and keep saying are good OOP practices. But of course, if you say any of this, you get the, yeah, but what else does it do? Like, what's functional programming ever done for us? So today we're going to talk about one of the other things, and hopefully you'll all go away a little bit kinder. And it's going to come in two parts. So the first one is folds, which it turns out is this thing the internet's obsessed with Ross Kemp's face. Like, I'm not making this up. I found so many, like, why would you do that to yourself? But someone did. More relevantly to this talk, we can think of it as array reduce. Folds actually are a bit more general than arrays, but we're going to be fine if we think of arrays for now. So here's array reduce, if you've forgotten what it does. You start with an initial value and a list of other values, and some operation, so we're going to use plus here. You take the initial and the first, you use that operation to get some value. You take that and the second, and combine them, and you keep going until you've got everything folded up, into one value, and that's your answer. But you can actually do a couple of cool things here if you know how your function's going to work. So if you have associativity, which is as long as your variables are the same left to right, you can put the brackets anywhere, you can actually break up this list into sub-chunks, and you can do parallel reductions, sub-reductions, and after that you can take your values, reduce all at once, and you get the final result, right? Because it's associative, we can do parallelism with no fear of what's going to go wrong. Which is cool. And the other thing we've got to talk about are monoids, which it turns out, I found out last week, are a race of aliens in Doctor Who, which has nothing to do with this talk again, so really sorry. We're going to talk about monoids as semigroups with identity, which probably answers one question and raises two. So semigroups are things you can append together. If you've got two things of the same type, you can append them and get another one. An identity is a thing where when you append it, it makes no difference to what you appended to. So because that's really confusing, take something like the sum monoid. Appending two sums actually takes the values out, adds them together, puts it back in a sum, right? It's the sum of sums. And the identity for sum is 0. 0 plus anything is the anything. It has no effect. Similarly, the product monoid would do the same, but multiplying the values. And of course, 1 times anything is the anything. So 1 becomes your identity. And that's pretty much it, except these two laws. The first one's associativity. Here's what that little bracketed thing looks like if you actually write it down. So you've got x append y append z, or x append y append z, right? As long as they're left to right, everything's fine, it'll work. The other one's this identity, and all that law basically says is it doesn't matter which side you put the identity, it makes no difference. Like, it's important to notice that what I'm saying isn't you can swap the variables around, just you can group them in any way. And that's all you need to know about monoids to understand the rest of this talk. So we've got this idea of monoids, we've got this idea of folds, and now we can put them together and make monoid folds, which is the creepiest picture I've ever created, so I'm really sorry. And it's actually quite straightforward. We start with the identity as our initial reduce value, we wrap up all the values individually, and then append them onto the identity. That's literally it. And this function will work with any monoid and any list of values because it's just completely generic with the idea of what a monoid is. And so we can write cool things that look like this. Fold up the list of 0 to 50 with the sum class, right? It's beautiful. And you get 1,275 and everything works and you tell all your friends and that's great. But possibly a bit contrived. So like first lesson is I want to see this in people's code, which is when you take your custom collection, some type with an internal iterator, instead of writing methods like getSum, getAverage, getMax, just write fold. And then we can pass in the method we want to use. The business logic is completely separated, which is cool for two reasons. First is it's declarative. I've literally said here, fold it up with the sum. And the second is the O in solid, which everyone seems to forget at convenient times. Open for modification, closed for, no, wrong way around. Open for extension, closed for modification. So if your boss comes along and you've got this getSum method and says, actually, I want the average, you've got to stick another function in there. If you use folds, you don't. You write your average logic completely separate from it, and then you just pass it in. The original class doesn't need to know you're calculating an average, it just carries on as if nothing's happened. And also, that logic you've written for average now works with any collection that has folds, because this whole thing's completely generic. So that's really cool. And this was where I was going to stop, but then I saw something cool on the internet, so we're going to carry on. Monoid folds look like this if you draw them in pictures. I hope the calibration's all right, but this is yellow and blue, and you mix them together to get green, right? Analogies. The point here is that the only thing that's variable, actually, when you do any monoid folds, are the two sides. The little bit in the middle actually never changes. It's always get the identity from whatever monoid we're using, reduce the list with append. So we all want to be OOP programmers because functional code does nothing useful. So what we'd like to do is we'd like to wrap this behavior in a class. And if we were to build this class, it would need three things. It would need to know what the wrap method is, how to put them in that box, what the monoid is that's used in the middle, like is it sum, is it product or something, and how to get the value back out. Because it's not always arrow value. There are some complicated examples we might have time to look at, but probably don't. And then you can do some other stuff, because you've all learnt functional programming, and you all know about algebras and type classes. So for example, you can apply a map method to it, because you know it's a covariant functor, right? Everyone nodding in agreement. Good. So string joiner is a fold that I just made up that takes a list of strings and just sticks them together. That's all it does. From left to right, just sticks them together. If I map over it with the string to upper function, what I get back is a completely new fold that takes a load of strings, sticks them together, capitalizes it, and returns that. That's all it does. It doesn't change the fold it had before because of mutability, that concept that functional programmers keep pretending they made up, but was obviously OOP. Doesn't violate any of that. It all works. And symmetrically, if that's like a post processor, so we change the value on the way out, we can change the values on the way in, because as you all noticed, it's also a contravariant functor in the first argument. So, for example, when we're calculating the length, actually that's just the sum of all the values if all the values were 1. So we could write a contra map that says every time I get a value, just return 1. So now I've got a list of 1s. If I do the sum of that list, I've got the length, right? It's just a consequence of having sum and that pre-processing. So we've got two different types of functors, and as you all know, if we've got functors as a base, we can start to experiment with the plicative functors. So based on what we know about map, we can take this function that returns another function, map over the list, and what we get back, in this instance, is a function that takes a number and divides the sum by that number. If we then give it the length, we get the average, sum over length, right? App actually encapsulates some really cool logic that takes both monoids, the sum and the length, puts them side by side in a pair, calculates both of the values at once, and then does the equation at the end. So whereas normally to do average, you'd map over it twice, you'd map over once for the sum and once for the length, this actually doesn't do that. This does it once and just calculates all the intermediate values. And because it's really ugly, right, and we don't like this, you just hide it behind a convenience method, because that's how we write all code. It's ugly, put it in a box. And if you build enough of these boxes as a grand finale, you can do actually quite complicated things. So you can say the standard deviation is all the numbers squared summed together, because we've got a contra map, divided by the length minus the average squared, square rooted. And the thing to remember is this only passes over the list once, from start to finish, collects all the values. We've never had to look at any of it. I don't know if you've ever tried to write standard deviation functions, but you either have a big ugly loop that you can't understand, or lots of little loops that are really inefficient. This solves both of those problems at once. It's beautiful. And as we can see, it works at the bottom because you just put a list of numbers into the fold, and out comes the right answer. So, if this is at all interesting to you, I built it. Go and play with it. It'll be great fun. And also find me on Twitter and ask any questions, because I love rambling about this. And because I've got to attribute my stock photos, rosskempfolds.tumblr.com. Highly recommend. It's wonderful. It's where I go for all my stock images. And that's all from me. Any questions? I was expecting heckling. I'd put it up there.
Whenever you apply a fold or other functional programming, then you lose all type information for what comes out the other end. How does that trade-off affect you in your day-to-day programming, where you're losing type information against being able to do clever?
So my favorite argument against this is that's PHP's fault, because Haskell will type that for me. Like, it will tell me what the value is at the other end. It's PHP's poor type hinting that means that's a problem. But the way I actually got around this, if you go and look at the implementation, is that all the monoids are built with factories. So actually, instead of having that type hinting there, the factory is what you apply with the types. So when it comes to the pairs for the applicative, that's the level where you say the left one's going to be a sum and the right one's going to be a product or whatever. And so that's where you would do your type checks, is you would say, actually, is what comes out still within keeping with the factory I used to get them in? I haven't written that, but I'm saying, you could, fairly trivially. Another one.
Have you seen the short Dojo RSA?
Yeah, I can't wait. I really can't wait. Because JavaScript makes this look beautiful, right? And if we look at, I've got to work this thing now. If we look at this is really ugly. Really ugly. And this use keyword, I hate it. Like, why isn't that implied? There was an X on the outside, why isn't it on the inside? So if that comes in, obviously this talk gets a lot better and people will actually start listening. Maybe. Anything else? No heckles. I slagged off everything you guys do. Okay, well, that's all from me.
Thank you.